harmonic motion. If I get through enough, I'm going to start talking about fluids, specifically pressure, and at the end I'll give you back your exams. Also, since most of you seem to run up in a frenzy, I don't like holding on to all of your homework. So for those of you who did not pick it up, this pile represents homework 4. This represents homeworks 1, 2, and 3. And also, as a reminder to everybody, someone forgot to put their name on homework 4. So if you did not find yours and you're convinced you did it, come here and claim it at the end, write your name and give it back to me. Okay. With that in mind, let me remind you of the derivation, because I did it quickly at the end of our last lecture, for the simple harmonic, the oscillatory motion. So sometimes this is also known as SHO, for simple harmonic oscillation of a mass on a spring. And here what I represent is that this is the equilibrium length of the spring, and that now I have extended it a distance x. Because I've done this, we already learned through conservation of energy, in which the potential energy of the spring is 1/2 kx squared, that is going to basically oscillate back and forth, going a distance x back to the equilibrium position, going a distance x, in this case compressing, and then just going back and forth, back and forth, back and forth. Where at these extreme conditions, the velocity is equal to 0, and at this area, at the equilibrium position, the velocity, sorry, is not 0, the velocity is maximum. And that can all be achieved by just saying 1/2 mv squared is equal to 1/2 kx squared. And that's conservation of energy. But that doesn't tell us the equation of motion, in which the equation of motion basically of interest here is to say, at any time t, if this represents the x-axis, how can I find its exact position? And so in this case, you have to look at forces. And so the force on a spring is negative kx, but that of course is equal to any general ma, which let me put as max. I'm going to skip the differential notation until the end, for those of you to realize where the actual math comes from. But setting them equal to each other, that means if I add kx on both sides, I have m multiplied by the acceleration, which I'm specifically saying is only in the x direction, of the mass m, plus kx is equal to 0. Dividing everything by m, I have the acceleration plus k over mx is equal to 0. Now let me define omega squared is k over m, which therefore means that omega is the square root of k over m, and we'll see in a moment that this is going to be our angular frequency. So now I have ax plus omega squared x is equal to 0. Or to purely understand what this is going to be, in differential notation, remember, velocity is the change in x over the change in time. That's what we saw. But for those of you who have already taken this, this is dx over dt. For anybody who looks at a higher level physics book, or if you're ever interested in that, this is also represented as x with a little dot. And this just represents the time derivative of the x variable, or the position. Acceleration, we've learned, is the change in velocity over the change in time. That basically is going to be the change, the rate of the change in position per change in time, which is just going to be in differential notation, d squared x over dt squared, which if you look in higher physics books, that's called x double dot, where each dot represents one time differentiation. And what I really want to show you is that any equation that looks like this, in which you have the second derivative, in this case it happens to be time, but it could be the second derivative with anything, plus omega squared in that same derivative. So here's position equal to 0, and this is the equation of motion that we get, that the solution for this is going to be x of t, because we're differentiating with time, because that's the relationship. X is related to velocity by the rate of time that you change the position. Acceleration is the rate of velocity per unit time, thus it's related to the rate of distance per unit time squared. That this is always going to give you the same equation, A, which is just a variable, cosine omega t, plus B, sine omega t. And anytime you have this standard equation, where you have the second derivative, in this case it's time, plus omega squared, that same derivative that you're differentiating equal to 0, you're going to get that variable which you're interested in, which we are positioned here, per unit time, because that's what we're differentiating it is always going to be equal to this. A cosine omega, so the square root of this, t plus b sine omega t. And for us, this is going to be, for the spring, A cosine, the square root of k over m multiplied by time, plus B sine, the square root of k over m multiplied by time. And that's where we left off at the end of our last lecture, by basically solving for this. I believe most of you have already done a lab in which you dealt with mass on a spring. I'm not sure how the lab write-up did. I think it did in actually a very good way. I think it did something similar to how I showed you here. But we found this equation of motion with the idea of forces. So let me find how we can find A and B for a moment. These are initial conditions. So what we basically want to say is, at what time t will one of them be equivalent to 0? So let's just say I brought this out and I just let it go swinging back and forth, back and forth. And I choose the time in which I say, now I'm going to choose time t, and forever after this position, I can find this position at any place else. So maybe it's been going for a minute, maybe it's been going for an hour. Without friction, maybe it's been going for 1,000 years. And I just come up and I say, I have my stopwatch, time starts now. Let's say it happened to be in this position, where the position on the x-axis is the equilibrium position, x of 0. That's what I call time t. So once again, it's me just specifying initial conditions, means I specify when I declare time equals 0. And I declare time equals 0 to be at that position. So if I want to find the equation of motion forever, all I have to do is say x at time equals 0 is going to be equal to A cosine omega times 0 plus B sine omega times 0, and I have specified that it's at this specific position, the equilibrium length x of 0. So here I define it to be at this position. The important thing about this is that, notice, this gives me sine of 0. The sine of 0 degrees is by definition equal to 0. So this term cancels out. So this allows me to solve for A. The cosine of 0, this is just equal to 1 by definition. So what I now have is A, because cosine is equal to 1 at this position, A is equal to x of 0, the equilibrium length. And now this completely collapses to say I can find the position at any time t just by being equal to x of 0 times the cosine of omega t, where this is just x of 0 times the cosine, where omega is just the square root of the spring constant k, divided by the mass m, multiplied by any time t I care about. So if I said, where will it be in 15 seconds? In 3 hours. All I have to do is put in the value t here, and assuming that you know k and m, i.e. omega, all you have to do is multiply it, get a number, find the cosine of that value, and multiply it by x of 0. So that's all that you basically have to do for this. And that will forever tell you the positions. Now let's say instead that I knew it was at some position x. Let's just say this is just some position x. And at the time that I saw it at position x, so I tell you here that when it's at position x, that basically means that the time is going to be pi over 2 divided by omega. So 90 degrees divided by omega, the angular frequency. And remember, omega is just the square root of k over m, so that's an actual number. So all I'm saying is that at this time, which I've just specifically defined like this, the position is x. So let me put it in. If I put it in here, then x at this time, pi over 2 over omega, this is equal to x, this is equal to a cosine omega times pi over 2 divided by omega, plus b sine omega times pi over 2 omega. Now the reason I did this is because the omegas cancel each other out. The cosine of pi over 2, which is 90 degrees, is by definition equal to 0. The sine of pi over 2, 90 degrees, is by definition equal to 1. And in this case, what I find is that at this specific time, the value is x, and this value, a times the cosine, is 0, so everything's 0. B times 1 is just b, so b is equal to x. And thus, forever now, I could say x at any time is just going to be equal to b sine omega t, which is just b sine omega for the spring is the square root of k over m multiplied by time. And that's how you would use the initial conditions of what's given to basically collapse this general equation, which is the general equation of motion for the position of the mass on a spring, to some specific value in which you find a constant. So let me actually, right here, I said b is equal to x. So if I just define it that way, then I can always know what its value is going to be. And thus, this is basically what you do. The forces give you the equation of motion. The initial conditions will tell you what the value of A and B are. And if they're picked in a correct way, then basically what it's able to do is kill one of these values. So that one of them is equal to 0, and thus for all time, it must equal 0. So this basically tells me if this equals 0 for all time, A must equal 0. If over here for all time, B must equal to 0. Otherwise, if it wasn't, the equation wouldn't make sense. And so this is what we see for these problems. So if you were given something that was in your lab and you said, where is the position at time equals 0, that's all you would have to do, and your equation would collapse to something that's simple. Of course, if you pick the initial time poorly, say something that wasn't at time equals 0, but also something that wasn't, say, something like this to kill the other factor, then you have still two unknowns with only one equation, and you could not solve it just with that information. So you would have to look at other sources. So usually the initial conditions would be chosen or determined in a unique way so that one of them gets killed off, one of these terms.
Why isn't x parentheses c equals x initial like that one?
What do you mean?
X sine omega t, right? Why isn't it x initial like for cosine?
Oh, just because I set the distances differently. What I said was, if it happened to be at this position, which I just said is the equilibrium position, when I said time equals 0, that's what I set it to be. So notice I say x of time equals 0 is equal to x of 0. So I defined that. Over here, I just said now it's at some arbitrary position x at a time that's pi over 2 divided by omega. So they're two different positions at two different times. But both of them say, at this time, in this case 0, it's equal to this. At this different time, it's equal to this. So just two different values. Perhaps it was the same. Perhaps I could have just said this tilt is x0, and this is x0 and x0 as well. So it's completely up to you. Well, completely up to me since I'm writing the central questions. But it's completely up to who's ever observing it to say 1 time equals 0, and what position you want to classify it to be. So if you're just watching it go by and go by and go by and go by, at any point as it's oscillating, you could say time equals 0 here, 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 and then you have an equation for effort to determine it. And that would be the one on the left.
What's the difference in the physical picture between A and B?
Nothing. Remember, this is our sine. This is the cosine. Cosine of an angle theta, sine of an angle theta. They are exactly the same, except they just happen to be off by 90 degrees, or pi over 2. So that's why cosine and sine are the same. And sometimes you would see this equation over here, this general equation written as a cosine omega t plus phi, where here phi takes into account both cosine and sine, and a is a constant. So instead of a and b being the constants, here a and phi. And this is typically known, if you see this, as a phase angle, which you will see in physics too, when you talk about coupled circuits, when you talk about a circuit that has, say, a resistor with an inductor, or a resistor with a capacitor, or a circuit with a resistor, capacitor, and an inductor. You will see that the voltage and current lag. One of them lags behind the other by a certain phase angle here. So this equation, which is the general thing for this, can also be represented by this. And it's basically all you do is you say, gee, if I just, in this case, let me add 90 degrees to sine. Then this position becomes this position becomes this position. And you did it. Or sine, if I subtract 90 degrees, everything shifts. This maximum becomes this maximum, this minimum becomes this minimum. The zeros correspond to each other. So they're really the same basic idea.
If you count the initial position as the midway, and we're going to have like in between both amplitudes, can you assume that the phase angle is 90 and just work off the cosine?
Yeah. That's an easy way to do it. Other questions about this? The spring.
Okay, so basically we're choosing a time so that we can cancel out one of these and have a set, like defined equation for any position.
Yeah.
Why can't we just go off of one of those equations?
No, because both of them are equally acceptable. So that is the most general equation to the solution to that mathematical problem. That mathematical problem, which is a second order ordinary differential equation, will give you two equations with two constants. And both of them, just based upon this equation, both of these are valid. It's the initial conditions of the physical system that will say if one of them or both of them should have a value. In this case, I've chosen it so that in the first one only A has a value, in the second one only B. But I could find it with a different time that both A and B both have values. And the equation could be some value A cosine omega t plus some value B sine omega t. So it's just a consequence that that equation always generates two results, and thus it's up to the physics of the situation, the actual experimental setup, to determine what those values are, and if you choose them correctly, that one of them will be equal to 0. Well, I noticed you had another lab. Some of you already done it. I think probably all of you have done it already, and that's a pendulum. A pendulum also exhibits this type of simple harmonic motion or simple harmonic oscillation. So let's basically look at what's going on here. So let this represent, say, a ceiling, for example. And what you have is a string. Let's consider it to be a massless string to make our lives easy for ourselves. So this is going to be a massless string of length L, and connected to that at the end, the bob, is a mass M. I now extend it from its basic equilibrium point, so this is what the dotted line represents, the equilibrium point, because This is where if you just let it go and friction actually holds, after enough time it's just going to be right here. I extended some angle theta. If I hold it here, i.e. if velocity is equal to 0 and I let it go, basically what happens is it's going to make this type of path until it swings to this other side where it should have the same angle theta, the mass m here, where the velocity is equal to 0 once again. And thus, similar to a spring, we go from velocity equals 0 to this point, the equilibrium point, where the velocity is maximum, to velocity equals 0 once again. And notice in the spring, compression and extension were both x. Here, the angle theta is going to be the same for each of them. In fact, you could find the velocity of this. Over here, if we did energy, what we would do is 1/2 mv squared is 1/2 kx squared. So the potential energy of the spring is equal to the kinetic energy of the mass. Here, if you did that and you wanted to find the velocity, and notice that this would also be a length L. This is a length L also. So let me call this a distance d. What you would now say is 1/2 mv squared is equal to mgd, where the general thing is the potential energy due to gravity, or weight. And notice because it's at a higher height above the surface, so if we consider this to be directly the surface, here it's at a height d. As it swings, it's constrained to still be a length L from the pivot point up here, so it'll always be a length L, but basically its vertical height is changing. Here it has 0 height, here it raises vertically, dips back down, here it vertically goes up. So you're seeing potential energy due to gravity, converted to kinetic energy, converted back into potential energy, and back and forth. That's why velocity equals 0 on both sides, because it's areas of all potential energy. And here it's all kinetic energy. Once again, it would be the same general idea, conservation of energy, that we dealt with a couple weeks ago. But I really hate how both your textbook and your lab manual deals with this. It sort of fakes it out. It sort of says, at a certain point, let's just call K the same thing as over there, and imagine there's a spring constant to the pendulum, which is completely unphysical. There is no spring constant that's for a spring. This has exact forces associated with it. So let's look at some of these forces that are associated with it. So let's take just a look at the extreme position on the right, where it's been extended by an angle theta. If we try to replicate it in the same way, notice what we did over there. The force Kx minus Kx is equal to ma. As we're going to see, we can't do that in this problem, but notice what we see here. The only true force is the force of gravity. That's what's pulling it down. Because gravity is pulling it down, it wants to fall straight down. But since it's actually tethered to the string, it's constrained to swing back and forth. Let's look at the sides. So right now what I've created is a right triangle. This is the angle theta. This is the hypotenuse length L. This is the opposite side, so this is going to be L sine theta. This is the adjacent, so this is L cosine theta. Now, if I dealt with forces, this problem would not work. So now, instead of dealing with forces, where I use the specific force on a spring equal to the general force ma, let me now do the same general idea except with torques. And of course, one of the definitions for torque is that it's equal to the moment of inertia I times the angular acceleration alpha. But here, let me just find the torque on this system right here. From that, we go from torque is Fd sine theta. Just ignoring the vector multiplication for a moment. With that, notice what we have. We have mg here. That's going to be the force, the weight. D, the displacement from the pivot point. This is the pivot point, so this represents the displacement. so that the displacement d is L sine theta. Multiply that by the sine of the angle between the force and the displacement. So this line here represents the displacement, this line represents the force, and thus the angle is 90 degrees. So the sine of 90 degrees, which we know the sine of 90 degrees is 1. So this tells us that the torque is just going to be mgl sine theta. And with this now, just as I did before, the specific force on a spring, Hooke's law, negative kx is equal to ma. Now I'm going to say the specific torque on this mass that's connected via length L to a pivot point is mgl sine theta. So I'm just going to set these two equal to each other. And what I'm going to say is I alpha is going to be equal to, and actually I've forgotten something, since it's pointing down, the force here is technically negative. So the torque is technically negative. Notice it's creating, in this case, as I'm showing you, a clockwise rotation, so that will give you a negative torque. So it's clockwise and thus negative, so that's why we have negative here. So I alpha is minus mgl sine theta. Well, I'm not going to go into it again, so refer to your notes, how I defined the moment of inertia. But for this system, the moment of inertia, in the same way I did the same exact problem with you in the lecture I did, I think, 2.5 weeks ago when I defined it. The moment of inertia I is going to be ml squared multiplied by